continue to discuss LC3 using assembly language, but getting closer to the hardware. We'll try to understand input and output. That's what I/O means, and a particular mechanism in modern computer systems that help manage a whole array of I/O devices, and that's called the interrupt system. So we're gonna just jump through the things that we already discussed and take a look at, let's say, how we are typing a piece of code into a computer like LC3. So here's one example. It's by no means an actual example of how the machine is built, but a conceptual example. Suppose I have these capacitors connected via a spring-loaded switch. And when I depress that spring, the switch closes, leading to charging of the set capacitor. And then I can go and read off the voltage of these ports, and we will say, oh, the zeroth element of it has a voltage of 1, which means that key is pressed. So that's just an example to show you one of the many ways external physical entities or quantities can be mapped into zeros and ones, and that's what we can deal with very easily. So suppose I have that, I have a system that does that, and I can exactly tell. Of course, real keyboards are a lot more complex than that. You can press multiple keys at the same time and so on, but let's skip all the details and just look at some simple principles. Then we can assume that I get an encoding, a one-hot encoding that says that's which key is being pressed, 1000. And what can you do about that? If you want to use a more succinct representation of which keys being, I want to turn that into, if I have 4 keys, what are the code that you would give to these keys? Probably 0, 1, 2, 3, right? Which correspond to 0, 0, 0, 1, or 0, 1, 1 encoding in binary. How do I get from here to there, right? Well, how did I go from there to there? That's called a decoder, if you remember. So conversely, if I want to go the other way around, it should be called an encoder. But an encoder has the following problem, that in practice, the space of trying to get, let me get this clearer. No. There we go. So the space of the input vector is far larger than the dense code, because I have 4 here. In theory, I have 2 to the 4th possible combination. And if I include it into 2 bits, that's 2 to the 2 possible combinations. So I have to do something, otherwise it will never work. And that's called a priority encoder. And the truth table is like that on the right-hand side. The priority simply means if there is a 1 at, let's say, the higher end of the bit, I don't care what happens to the rest. So let's take this example. If D5 is a 1, it doesn't matter what the rest of them are. They can be 0 or 1. I'm going to give it the code 101. So that's what priority encoder means. Now, think about that. This is just a condensed way of writing the truth table. Okay, what's the non-condensed way? Well, this entry will be 2 entries. Okay, it will be the 00010 and 00011. Those 2 entries. Similarly, this one would be expanded into many entries, into 2 to the 7th entries. That's 128. It would be 1 followed by a whole bunch of zeros to start with. Actually, 7 of them. To 1 followed by a whole bunch of 0 with a 1, and all the way to all ones, right? So in any case, you can fill this table. You can imagine, in principle, I write this thing out, but it's a very large table with 256 entries because there are 8 inputs. But once I have the truth table, recall back to earlier weeks, I think it was week 8 or something like that, or 9, where we figured out that if you can write the truth table, I can build you the circuit, right? That's what we guaranteed to be able to do. So then, the implementation, we can forget it. We can say, okay, we know how to do it. But how do I tell the computer? Well, you put it into a register. You put it into the register. In our case, I have so many keys, then we can assign 8 bits to it, and that's LC3, right? Then each key that had a character printed on top of that piece of plastic that the human being can see is in fact tied by the design of this hardware to a particular, let's say, ASCII code. Okay? That gives you an oversimplified and incorrect kind of description of what a keyboard can do. And then we know what key you pressed. Is that enough? Well, no, we had a keyboard status register over here. Why do we need that? Well, we do need that because to tell the difference between this key being pressed multiple times and just once. So we put a number in here. We say, oh, key K is being pressed. We set the bit to 1. And the computer will come, the operating system will read this to say, oh, I have a key. Let me read this off. And then go processing it to say a K has been pressed. If it's an editor, print a K on the screen and remember that the document has one more K in it, and we reset the bit to 0, and then when another K is pressed, this is again set to 1, then we look at it with, oh, that's another K. If we don't have the ready bit, we won't be able to tell how many consecutive Ks the same key has been pressed. And in LC3, the ready bit was set to be the top bit simply because it's easier. I can load the value. I can say, load the value from this register. How do you check the first bit? Well, it's easy. It's the sign bit. Okay, so you can easily test if it's positive, negative, or 0. Remember that? So if I check for negative, that means the top bit is set to 1. So it's just easier for testing. There's not much to it. You can really use any bit you choose. The code is just a bit more different. So I explained one output device, or input device actually, an I/O device. Can you imagine building others? If I have a touchpad, if I have some sort of pen system, touch screen, you can imagine that these are somehow translated into digital signals and communicated to the system via some sort of data register and a status register. So how do I organize them? Okay? Well, I organize them by remembering which register is tied to what hardware. So what we call keyboard data register is physically tied to the keyboard. And how do I read a register? Or anything, right? A memory cell. I need a piece of address. So there are 2 ways to do this. I can dedicate some address at the end of my address space. So that would be the top picture over here. I have regular memory, so address 0 is just memory. You put some stuff in it, you can read out, and so on and so forth. But by the end of the address, maybe I reserve a couple of spaces where really each one is special. They're not regular memory. You cannot, for instance, writing into this memory location has no meaning. Okay, we can make it, in fact, the register is not writable from software. It's only updatable, writable from the actual hardware. So you cannot use this to store value. Okay, it doesn't work that way. And when you read from it, you're really reading from the keyboard. That's the purpose. So, and all you have to do is to pay attention to not use these address for regular purposes. So when you load from address, let's say, in the case of LC3, we have the address something like a very large address, FDFF. 0 to FDFF. This is very large amount or percentage of it being regular memory, but starting from FE00, that's hardwired to some hardware device. So that's kind of approach one. Approach two, you can say let's create a separate address spaces altogether. So this is space 1, this is space 2. Okay, which is sort of like all the you give a different street name. This is no longer your main street. This is a different street, Maple Street. So now you have very few elements on there, but that's a different street. How do I tell which street, which address space that I'm accessing? By the instruction. So if I have a regular load instruction, that means I'm loading regular memory address. If I have, let's say, an instruction called load IO, for instance, then when it goes to load IO address 1, it means a different place than load from regular memory address 1. Okay? And in the case of LC3, we just had one address space, one instruction, just load. Well, not one instruction, there are multiple different loads in the code, in the instruction set. So how is this implemented? Easy. Remember our memory address register from LC3's hardware? We can decode. We can have some simple logic to say, is this greater than FE00 or greater than or equal to? If so, we're really accessing these special registers. If not, that address is used to memory to be loaded. So all we have to do is to use a mux to control. Okay, the address logic will say, oh, if I read FE I don't know, 00, then I'm taking this register's content out. Okay, and that's obviously implementable because I can write again a truth table, so I can implement it. Not necessarily optimized, but I can implement it. Now, the code, how do we do that? Now that we know we mapped it, and in the case of LC3, the data register is mapped to this address, the status register is mapped to that address. That's just designer's prerogative. I made this computer, I assigned it. Okay, not a big deal. How do I do that? Here's the code. There's the piece of code that if we run, we can actually see if the keyboard gave us something, and if so, what the actual value of the key is being pressed. So now we come to realize the use of this little weird instruction called load indirect. Okay? You probably still remember if I have just load R1 destination register A, what that does. It's PC offset. Okay? Compiler or the assembler is going to figure out what the offset of A is, and it will load from that memory location. So this value would end up into register R1 if I had the instruction load, but I don't. I have load indirect. So what that means is then the address FE00 that was supposed to be in R1, that's not enough. We're going to put it back into the memory address register again to load a second time. That's why it's called indirect. So by the time I'm done with that access, whatever is in that address, not this value, the content of that address will be loaded in. And what is that content? Look, this address is tied to KBSR. So this content, these 16 bits, whatever it is, will be loaded into R1. And very likely, it would be just 1 followed by a whole bunch of zeros. Okay, because all these bits are not used, they're probably tied to 0, which means ground. It could be tied to power supply, which means you will always read 1. In any case, we don't care about that value. We read the top bit is either 1 or 0. Because we loaded this value, the top bit, let's pretend for now, the top bit, the most significant bit is 1. Then the negative flag of the positive, negative, 0, that flag will be set because it's a negative value. This is a negative value. Look at this. It says if it is not negative, if it's 0 or positive, which means not negative, go back. Okay, great. This would just be a busy checking loop. Every time I'm checking, loading the status, is this 1? Is the bit 1? If not, I check it again. Okay? And when I'm done checking, let's say I get a 1. Then I move on. I start to execute this code. This time I'm doing load I R0B. So by now you know what happens. I'm loading from this address, which is the KBDR. So if this bit is set to 1, I'm loading these bits into my register. So that's all you need to do to handle hardware. Okay, this is how you read from your keyboard. Let's, for the sake of completeness, think about output, because this is reading from an input device. How do we write to an output device? Not very different. In fact, the starting code is almost exactly the same. I'm loading from a status register to say, are you ready? Are you ready for me to give you another character to print out? To print out onto the display. Okay? And again, if you're not ready, I'm looping. And when you are ready, I want to print something out by writing to the data register, let's say the ASCII code of the character that I want to print. And this time, the thing that we're doing is a store instruction, which is just about the opposite of load I. It doesn't store the value into memory address B, which is here, right? Which is here. It's not storing into it. It's storing into this address. So what it does is, in fact, it does a load first, loading the value from B into a temporary register, and use that as the address to store this content into that address. Okay, so you'll see input and output from the perspective of the CPU is really just the interface registers. Okay, sometimes they're more complex than that. There may be multiple status to show if the hardware is malfunctioning, is overflowing their buffers, or restarting, or whatever. But it's really the same principle. You get some status register tell you what's happening, and you have some data exchange register to communicate. And that's about it. So there are efficiency issues, we ignore all of that, and this is how you interact with the hardware. Okay, so there is a reason why these I/O devices are sometimes referred to as peripheral device. They're really on the outskirt, on the outside, not the core of your computer. They're slow. They're interacting with the physical world, especially with, let's say, human beings. Yes, your Pro display now can refresh the screen 120 times in a second, but your computer can execute 1 billion instructions in a second, okay? Not 120 instructions. So most of the time, the hardware, the I/O hardware, is slower. So if we really have code that does this, we end up doing nothing. We'll spend most of our time checking the hardware, and there's the problem, right? If I'm doing this loop, I'm not doing anything else. What about other I/O devices? Okay, so that's the problem. Compared to the core of the machine, CPU, and even memory, okay, even though memory tend to be a bit slower, the outside world is generally slow. That's not always true now. We have very fast devices now. Network, Ethernet card is one example. So there's more complications. So if you're familiar with the PC hardware, there's the CPU and there's what's called a chipset. And the reason it's called a chipset is because it used to be a set of chips. You know, someone handling this set of devices, another handling other devices, and at some point they used to be called a north bridge and a south bridge. The north bridge handling faster devices, south bridge slower devices. So there are lots of detail to that, okay, which really doesn't matter. The point is, in general, or at least to a lot of devices, they're really slow. We don't want the CPU to go actively polling each one. Do you have something for me? Because chances are no, right? Come back much more later. But when? It's also inefficient to guess. I don't know how fast you will be typing, and I don't want to come after a time delay to check. So we want the other way around. We want the CPU to be notified when something happens. So that's the concept of interrupt. Interrupt me when you have something interesting and I'll deal with you. So this is what it does, okay? We have the typical fetch the next instruction, execute it, and repeat loop. Now, before we fetch any instruction, we do a very quick check of some hardware that collects all the information about what device has some interrupt for me to handle. If there is one, I'll come and handle it. Otherwise, I will continue. So you might be asked, wait, then isn't this the same thing? Isn't this part done all the time and that's wasting time? Yes, it is kind of inefficient, but this was really done in hardware. Okay, so there's a bit. If the bit is not set, the rest of the financing machine will just do its normal business. Okay, so it's not the same thing as executing instructions like here. It's not this kind of polling. Okay, so it's still much more efficient. All right, so here's the high-level view. How does this work? Every device will have a trigger to tell you, hey, I have something, to tell the CPU. In fact, to tell the operating system running on the CPU, I have something. And because there are so many of them, any one of them, at any particular time in the execution, we may have multiple devices wanting to be handled. Okay, so we cannot handle multiple of them simultaneously. So what we do is to prioritize them. So you have a logic to select, okay, if two of you have interrupt at the same time, then A is going to be processed before B. And this is all summed up to one signal to the CPU to say, now you have a signal, you have an interrupt or not. And other than that, the CPU would just run its code. When there's an interrupt, we pause, meaning we have to somehow put the state somewhere. Pretend that we have a complete new slate, then we process the interrupt, and we come back, reload the state, and continue execution. That way, it looks like the interrupt didn't happen, other than the processing got delayed, but it didn't lose the state. Okay, so here's how you do that. Remember, we have the 15, the top bit, as a ready bit. Okay, so suppose we do that, then we have many devices, then we can just use that to decide who gets processed. Now, we may have finer control. We may allow the CPU to specifically shut down some devices. So then we expand that one bit. So we use the next bit as an enable bit. So this bit is what this bit, the bit 15, is generated by the hardware. This bit is written by the software, by the operating system. The OS will set this, let's say, to 0, which means shut up. Don't tell me anything. Then even if I have a hardware enabled 1, the AND gate will generate no interrupt. Okay? So this bit is called the interrupt enabling bit. Now, once we have that, we can apply this to many devices, give them priority level. This is something you figure out at design time. So you have 16 devices, maybe you give them 16 different priority levels. And then you encode them. Again, this is a priority encoder. So suppose, I guess here, higher is higher priority. So if this bit is 1, I don't care about these bits. My output is going to be 111, which is to say PL7, priority level 7 device wants to interrupt. And then you can say, okay, that depends on who am I serving at the moment. So this is new interrupt level. I may be processing some other things at the moment. Okay, so that's the priority of the current program. I may be processing nothing, but executing a very important piece of code. So I can raise my priority level. This is operating system detail. Let's say we don't have that. The only priority is which device level that I'm processing. Okay, so let's say PL7 has the priority, has the interrupt. Now I'm processing PL7. Okay, I'm executing code. So my current priority level is 7, and I reset the bit from the device to say, okay, I got you, but I'm still doing some wrap-up work. So I'm still not done. And then the hardware may already say, oh, then priority 4 has something to do. Since I'm still processing 7, say, no, hold on, I'm not processing you. So the interrupt is not going to be raised again, and only when I'm done, I will reset this to 0, let's say, to the lowest priority level. And then from then on, the new priority can come through to me. So this is obviously a simplified version. Here's kind of an early stage design. It's a patent from, I think, Intel. So you have your execution unit, the processor. What happens is there is a complete chip doing that interrupt control. You have many I/O devices, and this control sets that up, and it will only send a vector to the processor via a little bus, you can call it, and that's called interrupt request. And let's say you have 1001. Okay, that means I want to interrupt at a particular level, and then I can go execute the handler. So how do I know what the handler is? There will be an interrupt vector. Okay, we'll talk about that in the next slide. The idea is you tell me the vector, I will look up some table and know where to load from the program that handles that interrupt. So here's the example of vector. Let's say I have several priority levels, and I have all these interrupts. Code 1 for interrupt 1, code 2 for interrupt 2. I put them in these memory locations. Okay, they're not very long, I put them there. And then what do? I put this address into, let's say, vector 0, and that address into, let's say, element 1. So now I have a table. This is a vector because each one points to the handler address of one specific interrupt ID. So now, if we go back to think about the interrupt being sent to the processor, right? Here, I'm sending you a particular interrupt ID to say, okay, it's device 4. Now what I do is I go to element 4 of my interrupt vector, and then I say start to execute from that location. And that's really all there is to it. Usually, this is put at a very specific location, 0. So the job for the hardware is very easy. If I have interrupt 4, I will go to memory location 4, grab that address, and jump to the location to handle it. So that's really how hardware or I/O devices are being managed by the CPU. Okay, and we can see most of these low-level handling the nitty-gritty detail of the hardware is actually usually done at the assembly programming language level. Okay, and they are sometimes polled, but mostly managed by an interrupt-based system. And the interrupt logic has the notion of priority levels, has different sources, and there is a control logic that decides which priority gets handled at a particular point. And when that is clear, you know how to handle this, meaning you know what code to execute, and that's usually set up in an interrupt vector table. And that's a very specific code location that stores the actual entrance location of the interrupt handler. So with that, we know how to have hardware all working with the software. And by next week, we're going to look at more detailed view of how the operating system works. This is just one aspect of it, the interrupt handler or I/O handling in general.